Hello everyone, I'm here today to present my paper in Design Automation Conference 2021. My paper is called GNN4IP, Graph Neural Network for Harvard Intellectual Property Piracy Detection. I'm Rojin Yasai, a PhD student studying computer engineering at the University of California, Irvine. I work on the data-driven modeling and machine learning for different hardware and embedded system applications. The integrated circuits manufacturing industry has developed significantly and scaled down to 7 nanometer technology, which has made the integration of the numerous transistors possible. However, the hardware engineers could not keep up with the rapid advancement in the fabrication technology, and they actually failed to use all the available transistors in the die. To close this productivity gap under the time to market pressure, Harvard intellectual property core design has grabbed substantial attention in order to cut down the design cost and accelerate the design process. Globalization of the IC supply chain poses a high risk of theft for design companies that share their most valuable assets, IPs, with other entities. IP piracy is a serious issue in current economy with a drastic need for an effective detection method. According to U.S. Department of Commerce study, 38% of the American economy is composed of IP-intensive industries that lose between 2 to 600 billion dollar annually because of the IP theft, and which is mainly in the semiconductor industry. And all these results and reports highlights the importance of a method for IP piracy detection and prevention. So far, many IP security threats are discovered in the literature, and many countermeasures are proposed in order to defend these problems. First is the IP piracy, and the other problem can be the overbuilding, in which the foundry generates more IC than expected and try to sell them, and counterfeiting, another problem that in which the attacker produce an unfaithful copy of the pitch and try to sell it as the original one, and reverse engineering, in which the attacker retrieve the high-level information from the low-level design. The current countermeasures can be classified as detection methods and prevention techniques. Detection methods are watermarking and fingerprinting, in which the legal owner and the legal user of the IP add their signature called watermark and fingerprint to the design and use that to prove infringement. Prevention methods try to lock the designs or complicate it to confuse the reverse engineering, or in the split manufacturing, the IP design house split the ICs to have them fabricated in the different foundries, so none of the foundries have the access to the whole designs. Also, there are attacks so far introduced in the literature that try to bypass these countermeasures. For example, removal, forging, and masking attacks are targeting the detection methods, and they try to remove the signature, forge it, or mask it, and avoid the detections. Or, for example, the SAT and proximity attack try to unlock the design that is locked through logic locking. To overcome the shortcomings of current IP piracy detection methods, we propose a novel approach that instead of insertion and extraction of a signature to prove ownership, it models the circuits using graph neural network and assess the similarity between the IP designs. Modeling the Harvard design is challenging because it is a non-Euclidean type of data. That's why we first need to generate a data flow graph representation of the hardware, and then use the graph neural network to learn the hardware behavior from the graph level and generate an embedding for the circuits. Then we convert the circuits embedding to detect the IP piracy. We use graph representation for the hardware because both have a structural data structure, and it can be a natural representation for the hardware. Here we discuss the research challenges and the shortcomings of current methods in the literature for mitigating the IP piracy. First of all, scalability is a key characteristic for any hardware-related tool because ICs are getting more complex and integrating more transistors, and any approach needs to be able to scale to the large designs. But many of the current algorithms for graph similarity or formal verification are too complicated. And also another problem is for some of the method is that they require some manual review of the code, which is not feasible in practice. Other signature-based methods like watermarking and fingerprinting, they add a signature to the hardware, so they add an overhead to the hardware, which is another common problem. And also, they are vulnerable to removal, forging, and masking attacks. But our approach is pretty much fast, and also it doesn't need adding any signature to the hardware, doesn't have any overhead, and also it's prone to these attacks. It also be able to detect the IP piracy when the attacker has modified the design through obfuscation to complicate the design and make the detection harder. Another challenge is that different Verilog codes or if different graph representation may seem different, but in reality they have the same design. So the approach needs to be able to actually learn the behavior of the circuit to be able to detect the piracy, and by just comparing the look of the code or the topology of the graph representation of them is not possible to detect the piracy. We studied the concept of the piracy and similarity among hardware designs in a test case of two different variations of the full adder circuit. Here you see the schematic for a full adder circuit and two different Verilog code that are basically introducing the same design depicted in the schematic, but they have different codes. And we also have generated the data flow graph for these Verilog codes. The data flow graph expresses the signal dependency and the computational structure of the designs. At the first glance, the generated data flow graph for adders seem different, but with a deep look into the data flows, we can see that they actually representing the same signal relation. For example, the output signal sum depends on the num1, num2, and the Cin's input signals through data flow 1, data flow 2, and data flow 3 respectively. Suppose we focus on the critical nodes in the flow, XOR nodes, and ignore the excessive nodes related to concatenation and internal signals. In that case, the data flows in both data flow graphs represent the same operations. In this regard, we can see that how we can unveil the similarity between two designs using this graph representation. In the first step in our the IP piracy detection pipeline, we need to generate the data flow graph representation for the hardware designs. You can see the process of generating the graph for RTL code or gate level netlist here. We first pre-process the design to resolve any incompatibility and syntax error and also flatten the design. Then we use a hardware design toolkit called piracy to parse HTML code and generate the abstract syntax tree. And then we use the data flow analyzer in the tool to generate the signals data flow graphs. These graphs are just some trees that on the root we have each signal, and the graph shows the data dependency and computational structure from that signal to other signals. In the next step, we need to merge all these subgraphs to have one single graph for the whole design, and we also trim some of the independent part of a graph to make sure we have a one single graph for the whole designs. In this graph, we have nodes that can be represented signals, constant values, or operations or branches. Also, we have edges that are directed and they show the connection between one node to another, which basically showing the dependency of one signal to another one or showing that one operation is applied on a signal node. After the data flow graph is generated, we pass it to our graph learning pipeline to learn the behavior of the circuit and also generate a vectorized embedding for each graph, and then we compare this embedding to detect the similarity between the designs. See, I can see here the architecture of our GNN4IP model based on the graph neural network. First, we pass the graph representation to a couple of graph convolutional layer in which through a message passing process, they extract the features from the designs and learn the behavior. And in the next step, we have the pooling layer that works on the nodes in order to find which node has the most influence in the detection, and it put the attention of the design on those nodes. And after that, when the graph are pulled, we pass them through a readout operation which drains a vectorized embedding for each graph. So now we have a vector representation for each circuit, and we use that. We compare them using the cosine similarity, and we can assign a similarity metric between -1 to +1 to show that how similar are the designs. And also we pass it through a threshold block which decides if the piracy has happened or not. As I explained, our GNN4IP model generates a vectorized embedding for hardware designs and maps them to the points in the multidimensional space, such that similar circuits are in close proximity. We visualize the embedding using the dimensionality reduction algorithms such as principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE. This figure illustrates the embedding projection of the 250 hardware instances for two distinct processor designs, pipeline MIPS and single cycle MIPS. We have chosen here two processors that are basically have the similar functionality, but they are different in the terms of specification and design. So it would be harder for the design to actually differentiate into different processors. According to the plot, you can see that it has created two well-separated cluster of hardware designs that can be easily separated using a separator kind of plane or line, and it demonstrates that our model is a compelling tool to distinguish between various hardware designs, and it not only considers the functionality and data flow graph structure but also recognize the designs and specification. We have gathered a comprehensive data set of hardware designs in RTL and gate-level netlist to evaluate and train our IP piracy model. We gather data from the Trust Hub, ESCOS benchmarks, and also the online open source designs in addition to in-house designs. Our GNN4IP model examines a pair of the hardware designs and label them as piracy or non-piracy, and it also outputs a similarity score in range of -1 to +1, where the higher score indicates more similarity. We evaluate the model, and the results are shown as confusion matrix in here. We also calculate the accuracy as the evaluation metric, and it represents the correctly labeled sample ratio to all data. Here you can see that we are able to detect the IP piracy with very high accuracy, and the timing for each sample shows that the detection process is pretty much fast and is scalable for the large graphs as well. As you can see, the timing for the netlist in general is higher because the number of the nodes for gate level netlist designs is much larger, with around 3,000 nodes on average, compared to the RTL design with 1,000 nodes on average. To further analyze the similarity score generated by model, we have another experiment here. Our model identifies the piracy based on its generated similarity score for two design, and the decision boundary is controlled by a hyperparameter called delta. We tune the delta to achieve the maximum accuracy, but actually the user can adjust it to decide how much similarity should be considered as IP piracy. We calculate the similarity score in three cases in this experiment. In the case 1, we compare two completely different designs. In the case 2, we compare the two different codes for the same design. And in the case 3, we compare a design with its subset. And we have represented the score here. As you can see in the case 1, the score is pretty low, which shows that the designs are totally different. In the case 2, as we have the similar designs but different codes, you see that the score is very close to 1, which shows that our model captures the similarity with them pretty well. And in the case 3, we want to evaluate that what if that one design is a part of the other designs. For example, in the pipeline MIPS design, we have a unit called ALU, and when we compare these two Verilog code together, we see that the score is around um, 0.5, which means that they are not totally different, but they are not exactly the same. And it also very intuitive that we can actually find out if sub part of the IP is used in another design or not. To further evaluate our model, we tested it on a dataset of ISCA's 85 benchmarks and their obfuscation instances in the gate-level netlist format derived from TrustHub. Obfuscation complicates the circuit and confuses the reverse engineering, but it doesn't change the behavior of the circuit. Our model recognizes the similarity between circuits despite the obfuscation because it learns the circuit's behavior. We test this incapability in this experiment by comparing each benchmark with its obfuscated instances and computing each benchmark's average similarity score as is presented in this table. In the experimental results, all the similarity scores are very close to 1, which means that the GNN4IP can identify the original IP in a obfuscated design with 100% of the times, and it's resilient against the attacks when the adversary manipulates the design to conceal the stolen IP. Furthermore, we assess our model on the pairs of the different netlist instances, and the resultant average similarity is very low and closer to -1. It demonstrates that the GNN4IP is potent in differentiating the varied designs at the netlist level. Thank you very much for listening.